Good morning. So we are at the last class for Gaussian beams. So let's do a quick recap. We've started on Gaussian beams after looking at ray optics because in certain conditions it's necessary to take the wave nature of light into account. Okay, and we got a sense of where that is yesterday because we saw when we are focusing a Gaussian beam, only under certain conditions is the imaging equation similar to that we obtained when doing ray optics. We looked at Gaussian beams without going through a detailed derivation. So I gave you a set of equations, and what I want to do now is in today's class, really look at where we can use or how we can use those equations in different applications. Okay, so let's look at applications or application of the Gaussian beam equations. So I want to just write out some of the important equations. You had the equation for the beam diameter, beam radius. You had the equation for the radius of curvature. And I'm not sure if you remember, I had also very early on defined a Q parameter, and I said this Q parameter is actually a function of both R of Z and omega of Z, and we had given it appears in two different forms. I'll give you both of them. Okay. Or sometimes you will see it in this form also. Okay. Now, if you remember, Z0 was the Rayleigh range defined like this. So you can see that this term here is similar to this Z0, and so sometimes this is actually given as a right, where ZB is defined by this. So Z0 was a Rayleigh range of the confocal parameter. You can consider this to be a confocal parameter for omega of Z. So it's because it's similar to Z0. Now, depending on the application that you're looking at, you may have some information. So you can see you have omega of Z, capital R of Z, Q of Z, which is a function of both of these. There's Z0, there's omega naught. Depending on your application, some of this information may be available to you, and your application will require you then to calculate the remaining terms. Okay. So it could be that, so maybe you know Z and Z0. Right. Z is the location of the waist, Z0 is the Rayleigh range. So maybe you have that information, and you're being asked to find out what is the omega of Z at that Z value, right? So what is the beam waist there? Okay. It could be that you know the radius of curvature, capital R is a function of Z, I'm not writing that, and you know the ZB value. So that is, you know at some plane the radius of curvature, at some distance Z, you know the radius of curvature, and you know the beam radius at that place. Now you're being asked, where is the waist? Where is the waist? What size is the waist? Okay, and we'll see where these applications come. So as long as you know any two of these parameters, you can calculate the other parameters. Maybe you know Z and ZB. And here maybe again you could say, well, if I know Z and ZB, again I could ask, where is the waist? But maybe my application, instead of, so I could just ask, where is the waist? What size is the waist? Alternately, I could say, given this Z and ZB, the application requires a certain waist. Or requires the waist to be at a certain location. And then you could ask, what lens will do that? What kind of application could this be? Well, you could say, I have light coming out of a laser and I've gone through some optics. So I know ZB, right? Now I want to change that such that I have a certain waist size Y, so that it enters maybe, I want it to focus, sorry, I want it to be at a certain location, because in my system, say I have an endoscopic system for example, I know that the next element is going to be at a certain location. So I want it to be at that location. What lens should I use to achieve that? Okay. So like this, I've listed out some here, but I can take any combination. I could say I know Z0 and ZB, I know R and Z0. I can take different combinations saying, if I know two of these parameters, I can use all these set of equations in order to calculate the other parameters. And depending on each application, you will be asking that question. For in this application, these are the measurable parameters. This is what I know, and this is what I need to know in order either to make that application do something specific or to get some information from that application. So let's look at some examples. Okay. So the first case is a fairly simple case. Okay. Let's say Z and Z0 are known. This is example 1. So Z and Z0 are known. So for example, let's say you have a laser pointer. It's a green laser pointer. So let's say the wavelength is 532 nanometers. Okay. What do you want to do? Z is known. What you want to calculate is what is R of Z and what is omega of Z. Okay. So what is the radius of curvature? What is the spot size at that value of Z? Now, here all I have is a laser pointer. So when I say what is R of Z and omega of Z, basically I'm saying, if I were to point that laser pointer, the light across this room, for example, so I'm talking a few meters distance, what's the size of the spot when the beam has traveled a couple of meters? I might say, well, I'm going to sit in my office and I'm going to point it across to the tennis court across. Right? What's the size when it travels across, or from my block to another block? So I'm talking a little longer distance. Or I could say, let's point it up at the moon. What's its size at the moon? Okay. So calculate these three cases for me. Let's say we take Z as 3 meters, 30 meters, and let's take the distance to the moon. What's the distance to the moon? Yeah, so it's something like this. Okay, it's not, there are a few more 100 meters, but okay. So calculate for me quickly, right? If I just give you the numbers, is boring. Why don't you calculate? And let's do it. There's a number of you. So let's have the first row calculate the 3 meter distance. What do I want you to calculate? You don't need to calculate R of Z. I'll give you that. Calculate omega of Z. Okay. So you need some information from me to do that. I'll tell you that Z naught is 5.9 meters. And I've given you the wavelength. Okay. So let's have the first row calculate omega of Z when Z is 3 meters. Let's have the next 4 people calculate at 30 meters. So you're calculating at 30 meters, and the last row is doing it for the distance to the moon. Okay. Oh, sorry, yes, kilometers. Yes. So you're using this expression, omega of Z is omega naught. I had just written it down. 1 plus Z by Z naught, the whole square. So first thing you need to calculate is omega naught. So my Z naught is pi omega naught squared by lambda. So what do we get for omega naught? 0.99. 0.99 what? Okay, then do one thing, calculate this also for me. For these 3 distances, you can do this calculation. Let's also calculate this approximation, where if we assume Z is greater than Z naught, then omega of Z will, so the term Z by Z naught the whole squared is much larger than 1, right? So then I'm going to just ignore the 1, right? So then my omega of Z will reduce to Z by Z naught. So calculate this. Right now, just take this approximation and calculate it for all these 3 cases. So we can compare the approximation with the actual value. I'll give you the value of R. I mean, you can check it later. Omega of Z is 1 millimeter. Okay. Do I have a value for 30 meters? 5 point. It's just 5 millimeter. Okay, let's put 5.1 millimeter. Approximate. It doesn't matter if these are not exact. The idea is to get a sense of how things are changing. Okay, I'm not worried about the accuracy to several decimal places. Okay, and what do you have for omega of Z for the distance to the moon? 63.4 kilometers, right? And do we have the approximate values in each case? I am going to write it down because it's taking too long. Again, don't worry if these are not exact values. You can calculate the exact values. Okay, so what have we done with this exercise? I've been giving you equations endlessly over the last few days. I just wanted you to get a little familiar with those equations. So in this case, you were given 2 parameters. You were given Z. In other words, when you're saying given Z, you're being told at this Z, find out something about the beam. Okay, so that's what I mean by given Z. But what you're really given as a piece of information is the Rayleigh range of this beam. The moment you're given Z naught, and of course implicit in all of this, I didn't mention this earlier, you need to be given the wavelength, because if you're going to use Z naught anywhere or omega naught, this relationship between omega naught and z naught, of course you need the wavelength of the light. So this example was of a laser pointer, so we took something in the visible region. With the lambda, with the z naught, you can calculate omega naught, and with that value and the other parameters that are known, you then said for different values of z, what is the beam like. Okay. Now you look at this. At 3 meters, so you started out with an omega naught of a little under 1 millimeter. So it's leaving at the beam waist, it's less than a millimeter. It travels 3 meters away because your z is always measured from the beam waist. So it travels 3 meters away and it's 1.2 millimeters. Now, what is z naught here? Z naught was 5.9 meters, right? So you have a beam. This is omega naught. So this is z equal to 0. This is where you have omega naught. At this place, omega naught is 0.9 millimeters. If you go 3 meters away, okay, your omega of 3 is 1.2 millimeters. So the beam has hardly diverged, but you should not be surprised because the z naught of this beam was 5.9 meters. So you expect that the beam diameter stays more or less in that region, right? The large divergence is going to happen beyond z naught. That's why we call z naught the depth of focus, because there's so little change in that region. So the moment you were asked to calculate, if I had asked you to calculate for 1 meter, for 2 meters, for 3 meters, this is all less than the Rayleigh range of this beam. You should not expect a large change from the omega naught value. Depending on your application, you might say, I don't even need to calculate it. It depends on how fine or sensitive an application or what you're working with. But if you just needed an approximate number, you would just say, I know omega naught, I'm going to assume it's more or less constant over the Rayleigh range. This is, say, I'm using the beam here and I was pointing at the screen. It's a couple of meters distance. It's not that the beam diverges very much from when it leaves a laser to when it reaches the screen. If I were to send it across one building to another building, now it's traveling a greater distance in tens of meters. And there, even there, the omega of z is still fairly small, right? But you see, when you go the distance to the moon, right, what has happened there? You have huge, you're talking about, I mean, the units are changed. You've gone to kilometers. And it's not surprising considering the distance. You were talking about meters, units of meters, and now you're talking 384,000 kilometers, right? Of course, the beam is going to be very large. This example is to give you an idea of how the sizes change or why you might want to calculate the radius at different sizes. Of course, you would not be pointing a laser pointer at the moon. Well, you could point a laser pointer at the moon. What would be the problem? You wouldn't have enough power reaching the moon, right? Because now the power that was in that beam of omega naught size 1 millimeter, that power is spread over 63.4 kilometer spot size. I mean, you're not going to get enough power to have anything measurable, and it would be impossible if you said that's getting reflected and coming back, you would really have no power. Okay, so this is just an exercise to give you an idea of the numbers or the sizes. It isn't practical. The last part isn't really practical in terms of the power of the source that you're using. Let's take another example. In this case, let's say R and ZB are known. That means this R of Z is at some plane. So at some plane Z, radius of curvature is known, and pi omega b squared. So I know the local size of the beam, I know the local radius of curvature, okay? And I'm focusing this beam. I might ask, given that I'm focusing this beam, where is the location of the waist? In other words, what is Z? Right? I can also ask, what is the size? No, I know ZB. So what is the size of the waist? Now, an example of where this might be used, let's say you're using a laser radar system. So it leaves, and you know the size, the radius of curvature and the size of the beam when it leaves. You have optics, it's focusing it. You need to know where the focus is. Why? Because that's how the radar works. It focuses on some object, and then that focused light is reflecting back, and you're sensing that focused light, and from that you are able to tell where the object is. Okay. So in such an example, what kind of laser would you be using? A very common laser to use is a CO2 laser. CO2 lasers can laser at different wavelengths, but let's say you're using this 10.59 micron line of the laser. Okay, so it's in the infrared, and the beam has been expanded to this size. It's quite a large beam, quite different from the case of the laser pointer, where omega naught was 1 millimeter, right? You've been given what is known as ZB. That means this is given to you, right? This is your ZB, and this is given as 6.6 kilometers. R has been given to you, the radius of curvature, and I'm going to say it is minus f. F is of the focal length of the lens that you are using. Why is it minus f? Because if you think about it, I'm talking about a converging set. So that my negative sign there is indicating that this is converging. Okay. Now, in order to get useful information out of this, we are going to use the Q parameter. So you remember 1 over Q, I will not write Q of Z, R of Z and so on, okay. Please remember, these are functions of Z. I had minus J pi omega B squared lambda, right? Or let's for the first part, let me write it just in terms of ZB. Okay. I haven't directly been given omega naught, but I can calculate omega naught. Why? Because Q is also Z plus JZ naught. So if I can extract, I know R, I know ZB. So if I rewrite this 1 over Q expression in this form, I can get Z naught and I can find out omega naught, right? And that's what I want to do. I want to find out omega naught and I want to find out Z. Where does that waist occur? So I'm going to rewrite this equation 1 over Q. So 1 over Q will be ZB minus J JR or Q is ZBR we're just setting it up so that we can extract the real and imaginary parts. So I have ZB squared R by ZB squared plus R squared minus plus J R squared. So this is nothing but Z, and this is nothing but Z naught. Right. So I can write Z, and I'll just divide everything by ZB squared so that I have it in this form. And Z naught will be ZB 1 Now, if you remember, when I gave you the information about this problem, you were given ZB and you were given R, and we had taken R as minus F. So I'm going to substitute now. That's a given. Remember, the givens of this problem are R and ZB. So given that R has this value, Z is going to be minus F 1 plus F pi omega b lambda the whole squared. And I can use this, ZB has been given to you also, so I can use this. But in principle, I have got the information that I wanted. I said for a given ZB, for a given R, I need to find out omega naught, and I need to find out where the waste occurs. In other words, I need to calculate Z, and that's what we've done here. Okay. But it's interesting if you look at what happens if you change the lens that you're using. Okay. So we said for a particular lens, we had set up the system such that R was minus F. So you can say what happens when I change the lens, and if you do that and plot a set of curves using these equations, but you plot how Z, so this is distance to waste. Okay, that is minus Z, and this is F. And in fact, if I plot it for this particular example with the numbers, you're going to get something like this. And this is an interesting result, because what am I plotting? I'm saying as I change F, I'm changing, of course, where the waste occurs. That should not be surprising. But this tells me that to get a waste at a particular location, say my goal was to get the waste at a particular location, at a particular value of Z, there are two different values of F that satisfy that. Pardon? No, I'm changing, well, F appears in various places, right? So I'm changing, when I change F, I am changing, R is also changing. Yes. Yeah. So this is telling me to get a waste at a certain location, there are two ways of doing it. And if I plot for the same range of focal lengths, the waist diameter, the waist size, let's say the waist diameter. Okay. By the way, if you solve this for the problem that we are discussing with those numbers, this distance to the waist is going to be in terms of kilometers. This is in terms of kilometers. It goes from 0 to about 40 is this, and this waist diameter is in centimeters, and of course I'm plotting it for the same set of focal distances. So it's about, okay, and it's going to do something like this. So what is this telling me? That if I wanted the original goal, or the original way I stated this problem was to say that given R and given ZB, given that you know the radius of curvature and diameter of the beam at some location, what is the location of the waist and what is the size of the waist? And we calculated that. But we are talking about, in this example, a lens that beam of light that is being focused with a lens of focal length f. And now we're saying, if I change my question a little bit and say I want the waist to happen at a certain location, what lens should I use in order to get the waist at that location? It turns out I have two possible ways of doing it. And if I look at these two graphs together, you can see that the initial value here corresponds to a lower value of focal length, and this value corresponds to a higher value of focal length. So if I look at those corresponding values here, maybe they correspond to somewhere here and somewhere here. Now, what does a lower value of focal length mean? If I have an optical system and I have a lens with a small f, what does it mean? It means you're talking about tight focusing. Because if you had a collimated beam incident on a lens and the focus point is close to the lens, it means that's a lens with high power. It has to very quickly bring the beam to focus. Right? If I have a large value of f, you're saying that it comes to focus much after the lens. So it's the power of the system is less. I can consider this to be similar to a region of geometric optics. I'm focusing as I would in geometric optics. And this is more like I've got a collimated beam and it's got a fixed diameter. Okay? But the point is, if the goal, if the mandate had been find out what I should use, what lens I should use such that the waist occurs at this particular distance, you have an option of saying I will either use a tightly focusing system to do it, or I would use the Gaussian beam in its almost collimated form. Okay. So again, depending on your application, you might decide to use one over the other. So this example I wanted you to look at to show you that it's sometimes instructive to plot these kind of graphs, because it tells you or gives you some more freedom that you have with your design. You're not stuck only with one type or one way of solving a problem. You may have more than one way of solving a problem. Okay. I'll not do the third case in more detail, but a third example would be similar to second example. Okay. But let's say in this third example, so again, let's say Z is known, and as in the previous case, ZB is known. So you know the local beam diameter. Okay. And as I had mentioned in the discussion we've just had, perhaps in this case, you want the waist. So the requirement is that the waist is at a specific location. So here you could look at it at another way. If I go back to this equation, omega of z is omega naught 1 plus z by z naught the whole square to the power half. I could rewrite this. So let's just square it initially to get rid of that square root. And multiply it by this so that I can write it in terms of, so this is nothing but my ZB, this is Z naught, and this is Z squared plus Z naught squared by, in fact, let's just write it like this. So this equation can be rewritten so that it is in the form of a quadratic in terms of Z naught, right? Which means when I solve that quadratic, I'll again have two solutions for it. And you want the waist at a specific location. So you would look at those two solutions and see which one matches your requirement closely. So the point to take from all of this is, unlike geometric optics where you mostly always have very specific solutions, here we're saying just because of the nature of the beam, the way you arrive at a solution could be quite different. Okay, so here if you were, again, a good example as I had said is if you were trying to solve something for endoscopy, you know that you want the waist to be at some location, can't be very far away. So when you solve for the quadratic equation here of Z naught, you will get two different answers and you will pick the one that more suits your application, more suits the distances that are relevant to you. So for example, if it's endoscopy, the distances you will be talking about maybe in microns, in tens or hundreds of microns. And when you solve for the quadratic here, you may get one Z naught which is in microns, maybe tens of microns, and another one which is in millimeters. And so for this particular application, you may say this is the solution that I want. And therefore, based on this, what is the lens that I will choose? That gives me this solution. Okay? Okay, so I hope in this discussion, you've got a sense of how you can take all these equations that I've been throwing at you over the last few classes and play around with those based on your application, based on the knowledge that you do have, to calculate the other parameters which you need for whatever it is you're trying to do. Okay? Okay, any questions till now? Yes. Previous example. Pardon? I'm plotting. So once I have, you've been given, in this case you were given R and ZB, right, at some plane Z. From this you are able to calculate Z naught, that gives you omega naught. You are also able to calculate Z. So you know where the waist is occurring, you know the size of the waist. Once you have this, then you know everything in this expression, right? You know everything in this expression, isn't it? That's omega of z, yeah. That's what's plotted on the y-axis. Okay, so the last thing I want to do in this class is work out one more example, and that is to do with what is called beam relay system. Okay. Now, when we want to send light from one place to another place, you know the problem is that it diverges. So we have looked at, if you want to send the beam a very long distance, and it's a Gaussian beam, what you would do is to use a beam with a fat waist, because then its divergence is going to be as less as possible. But you saw that even if you do that, if the distances are fairly large, the example to the moon, you can never compensate or completely get rid of the dimension. You're never going to have a beam of usable dimensions, right? So typically, and for example, if we are saying all the light that comes through, for all our information that comes through the internet, for the internet, all of that is coming through fibers. So what people do then to send light a long distance is to send it through a waveguide. What does the waveguide do? The beam has this natural tendency to diverge. The waveguide has some property that compensates for that, and therefore the beam is kept in as an acceptable size. Now, the example I'm going to talk about now is, again, just to further your understanding, is not that this is really used. The fiber is an example of an enclosed waveguide. But I could also use some idea, concept of waveguiding in free space. So if I had a beam that's diverging, I could then use a lens, and that's going to compensate for that divergence. But of course, once it's focused to the beam waist, it's going to diverge again. So you put another lens, and in fact you can do what's called a beam relay by having a number of lenses. Okay. I haven't really drawn this correctly. Let me correct for that, because what I'm saying is I could do this, but of interest really is to keep it the same between all these relay lenses. Okay, so we are saying we have the same distance d between all these lenses. All of the lenses have the same focal length f, and our goal is to send the beam from one place to another place and maintain its size. Okay, so in a sense, it's like a free space waveguide. Now, if I say this is what I want to do, in other words, we are saying that if the beam had a spot size omega naught dash before a lens, I have set up my system such that the spot size omega naught after the lens is equal. So if I said this was omega naught 1 and this is omega naught 2, and this is omega naught 3, and so on, I'm saying omega naught dash is equal to omega naught 1 is equal to omega naught 2 is equal. So that's what I want to do. Okay, and it turns out that you can do this, but only if a certain condition is met, and that condition is if d is less than or equal to 4f. If this condition is met, then you are able to achieve this. Otherwise, you're not able to achieve this. So how would you prove that? How would you prove that? Can you tell me how you would prove it based on, think of the lens transformation equations that you were given. Okay, I see that we've run out of time. So this is just the last example that we have to work out. We'll do that in the next class. Okay.